Ira is the principal founder of a company called Semantic Designs in Austin, and he's been working for over a decade on tools to handle how to analyze and maintain large software systems. So I invited him over to give us a talk about the stuff that he's been doing to see if any of his ideas or tools could be applicable to software systems at Google. So Ira.
Hi, good morning. I'm Ira Baxter, CEO, CTO, Chief Bottle Washer for a small company called Semantic Designs in Austin, Texas. We're very interested in dealing with large software systems. All right, we all see that software systems exist. Okay, if you look at the ones that run large corporations, you discover they're actually very big. And they're not getting smaller, they're growing. And so the problem is we kind of see it is sort of indicated by this galaxy. You know, you're at some point here where you can see this very large piece of software, and it's enormous, and it's getting bigger. And the question is, how are you going to deal with that over the long run? So I'm going to talk to you today about tools that we have been designing and building. It's actually for about 15 years now. Okay, what I actually say to people is I'm 15 years into a 5-year technical plan. Okay, to give you some idea of what we think these tools might look like and what kinds of things you can do with them. So Semantic Designs, we think our goal is to change the economics of how software is built, at least for large-scale software. Okay, if you build things by hand the way the Egyptians did, it's going to take you 30 years to build a pyramid, 30,000 slaves. By anybody's standards, that's truly expensive. If you want to change the architecture of the pyramids, that's just not a good answer. Okay, that's not going to work. You need to do something different about it. The method is obvious. Bring machinery to the table. Okay, you need automation to make this kind of thing work. So we say, all right, bring automation, and what would it look like? Okay, the company was founded in 1995, okay, off of a core idea called DMS, which I'll talk about a lot during this presentation. Okay, and since then we've been trying to enhance this engine, put features in it and facilities to help us deal with these large systems. We're small, about 10 people, okay, but half the staff are PhD level computer scientists with various backgrounds in operating systems, software engineering, AI, theorem proving, so on and so forth. Okay, so it's an interesting crowd. They're a good crowd to work with. Okay. Now, a lot of companies, a lot of investors ask us, well, you specialize as a company, you specialize in software. What kind? They want to know if we specialize in banking software or embedded software or medical software. No, we specialize in software, okay, in big pieces of stuff, because there's a whole lot of machinery required to deal with just the software in terms of its scale. So we're not specialists in any problem area. We're specialists with software systems in general. Right, now, the tools that we apply our activities to are broad spectrum as a consequence. Okay, they go from embedded systems to aviation and military software to large-scale banking. It's all across the map. It's kind of surprisingly broad, and you'll see a whole bunch of examples that I go through here today. And we use these tools to carry off activities like architecture extraction, re-architecting software that is changing its shape, restructuring it, right? Translating from one language to another, and carrying out things like code generation. That's a very high-level view. So we see software everywhere. Interesting systems have oceans of code. It's easy to find million-line systems. And when you find them, what you discover is they're million-line systems, but they're coded in 5 languages. And they're all connected together in complicated ways. And they're not only running on this machine, but they're spread across other machines, and they communicate through distributed methods, and mailing files, and doing FTP, everything you can imagine. So the challenges when you face these kinds of systems are, how do you build this in a timely way? This is a problem software engineering still doesn't know how to do very well. Right? How do you understand the artifact that you built if you're going to make any kind of changes to it? Almost every organization that has a big piece of software will tell you that nobody here knows what the software does because all the people that built it left or are dead. Right? So how do you deal with a thing you don't understand? What do you do? Right? How do you deal with the quality of this stuff? If this thing is running your corporation and it's broken, your corporation's going to hurt. Right? This is a pretty strong theme for upper management. Software quality needs to be good with your large systems, or it's not good for the company. How do you make small changes, the kind of change that people do every day? How do I hammer on some little piece of it? Okay, and how do I make massive changes? How do I reshape the system to meet the needs of the future? How do I switch from a mainframe-based system, say, to an internet-based system? Or go from one data model to another kind of data model? Or take 2 data models from 2 different kinds of systems and merge them together so I can get a system which is smart across 2 kinds of data. Right? You want to make all these changes of some kind, you need automated tools to help. So how do we do that? Well, we fundamentally offer two kinds of support activities and tools to help people carry off these kinds of, deal with these kinds of issues. The first one is analysis. Okay, help organizations with large amounts of software kind of get it under control. Help them understand how the pieces are hooked together, what information is flowing from one part to another. Right? The second thing is help them understand what the quality levels are. Help measure, is this code good for some definition of good? Is it good because you've tested it well? Is it good because it's structured well? Is it good because it has a good architecture? Is it good because it's layered well? Right? So analysis is pretty big. Most of our customers, when they first come talk to us, want to know something about what they have. Tell me about what I have. But the question is why? Right? Analysis is an interesting topic, but nobody does it unless they're afraid of the answer. When you go to a doctor, okay, and you're feeling ill, you want an analysis. Doctor, tell me why I'm ill. Tell me what disease I have. But he can give you a very long, complicated definition of your disease, a very long, complicated name, and he can describe it to you. Okay, and if at that point you leave the doctor's office, the visit's really unsatisfactory. Nobody really wants to know what the name of the disease is. What they want to put is a label on the name so that you can do something about it. It's the cure that matters, not the analysis. So analysis is done to support change. So the other thing that we do, and I think the thing that makes us really, really unique, okay, is carrying out mass change to large systems. Use analysis to drive change. Okay, so do code generation, okay, from some kind of a specification where the analysis might require you to do, say, domain-specific analysis up front to invent a DSL, so you can do code generation from that. All right, restructuring, take your system and re-architect it, okay, to make it more useful. Modernization, rip out some kind of underlying piece of technology which this piece of software depends upon and replace it. So remove green screens and replace them, okay, with HTML. Move a hierarchical database and replace it with a relational database. Switch from a single-threaded system to a multi-threaded system. These are all massive changes, and they're not the kind of things that are easy to do by hand. Okay. The last one is like migration, okay, converting from one system to another and changing platforms while you're at it. So I'm going to give you some examples of analysis and change that we've done on various kinds of tasks, some very quick ones. Okay, and then I'm going to talk about the technology we use to do that. So on the analysis side, okay, here's a customer came to us with an IBM mainframe system. Well, they kept the mainframe in Australia. And they said, we have 10 million lines of COBOL. Okay, 3,000 JCL scripts, okay, 6,000 input-output screens, 500 databases, and we don't know how any of it's tied together. So when they want to do simple impact analysis, we want to change the way interest rates are paid to our customer base. They, first of all, struggle to find a place to start. Well, we think this database holds interest rates. And now the question is, what other parts of the software talk to that database so they can think about modifying it? Not so they can actually make the modification, or actually architect them, but what pieces touch it so they can actually start thinking about the impact analysis. If you cannot do this on a very large scale, you cannot schedule things well, you can't time it well, you don't know what your effort levels are, it's going to hurt you with quality, you're going to get hurt when you install it because you didn't think it through, because you didn't find everything. Just finding all the pieces and talking about how they're connected is a really hard problem. So one of the things we did for them was we built them a custom analyzer that reads COBOL at the 10 million line scale, that's 8,000 COBOL programs. It reads all the JCL, reads a peculiar thing called HoganDB. This particular application system is called Hogan. It's a banking system that you can buy commercially from CSC. And the Hogan system happens to be an architecture that makes it really hard to see how anything works. It contains a bunch of metadata that says all these programs talk to each other through the way this metadata predicts. So in order for them to see what's happening, you have to understand how the COBOL programs talk to each other, how they talk to the databases, and how they're directed by the metadata in the Hogan database. And so we built them a custom tool to read all that stuff and give them an answer. And I'll show you what that looks like in a little bit, okay, to give you a sense of it. The main point is it's 10 million lines of code. It's bigger than you are. If you try and pick it up, it'll squash it, right? So you need machinery to do that. So that's the analysis side, okay? They're struggling with just understanding what they have. Their next question is going to be, how do we make this thing better? That's the next step. This is a more interesting example, okay? You're not supposed to be able to see that airplane. All right, this is the B-2 stealth bomber, okay? B-2s are made out of essentially stealth materials and software. Right? So half of there's about 150 microprocessors in an airplane. Okay, it's a 25-year-old, 30-year-old design at this point. So it's using the best microprocessors you could get in 1975. Right? It has 16-bit CPUs that actually do floating point in the hardware. I didn't know you could get CPUs like that in 1975. But if you were the Air Force and you were building this thing, you could get that kind of stuff. So people wrote software to run this airplane. All right, so there's software to run the ailerons, there's software to run the engines, there's software to manage the airplane, fly to Baghdad, drop a bomb, come home. The pilot doesn't do anything except for say no. Right? The airplane goes down some path or somebody says abort the mission, he says no, go around. The mission software basically runs the airplane. The Air Force thinks this is a really interesting device for sort of forward force projection, okay, and they would like to integrate this device into their quote-unquote battlesphere. It's amazing what kind of terms you come up with when you go visit these different arenas. They want to integrate in their battlesphere, and all they have to do that is to take the software which is running in an airplane that was designed in 1975 and didn't know anything about the internet, okay, or radio links or communications, and replace it by something they can enhance. So this software is written in something called Jovial, Joule's own version of the International Algol language. Designed by Jules Schwartz, it was the best embedded programming language you could get in 1973. That was before anybody had ever heard of C. Right? The good news was they had 1.2 million lines of code that ran the airplane, did the mission software, all written in this thing. It all works, runs the airplane, everything's fine. The bad news, the people that wrote it are retired or dead. The development tools on which it was built run on VAXes. So the development tools are written in software for a machine you can't buy. You can't even find them anymore. Okay, so this thing was a disaster of first magnitude in terms of dealing with. They had to get out of Jovial into, if you like, anything but Jovial would have been their goal, but they were happy to go to C. Here's a complication. This is black code, top secret. We, SD, aren't allowed to know what's in it or see it. Can you please convert this to C without making any mistakes? The answer is yes. Okay, all you need is enough automation, and you can do that. Okay, so it's 100% automated conversion. It's now flying in the B2s that are being used around. We're very happy with this particular thing. Now I have to kill you since you've seen the airplane. Okay, so we've seen an analysis example and a transformation example, okay, to give you an idea of the kinds of things that we do. So let's talk about how we do that. Okay, now if you had to build a tool to build each one of those things, each one of those the analysis engine or the B2 thing, and you had to build it from scratch, you'd simply die. Okay, there's just too much machinery involved in doing that. We have a very simple insight. And the very simple insight says that when you build large, complicated tools for dealing with software, that much of the infrastructure they have is the same as every other tool you build. Okay, you need parsing, you need analysis, you need this and that. You're going to hear that theme a lot in this talk. So we did a simple thing. We built an engine that has a lot of shared infrastructure. Think of this as an operating system supporting application programs, which are software engineering tools. So that's what DMS is. It has this long, complicated name, which is another hour talk as to how it got this long, complicated name. Okay, so its official name is DMS Software Reengineering Toolkit. We call it DMS for short. Okay, so what is this? So it's a device, not for being a tool that does something directly. It never does anything by itself. Okay, what it does is it manufactures the tool that does what we need. So you can think of this tool as being something that takes in a bunch of description, a bunch of raw materials for describing what has to be processed, and spits out a device for carrying off a specific task at hand. So what we actually do is we take DMS, we manufacture a tool with DMS, and then we apply the manufactured tool to the problem task. Okay, and the good thing is we can use the raw materials for DMS over and over again. Now there's a list of applications over here on the left. Okay, it talks about various kinds of things we've done. Formatters, migration tools, test coverage tools, code generation from C++. And I'm not going to describe those in any detail here. What I want you to do is see that that list is long and they look really different. Okay, and you wouldn't have guessed if I hadn't probably preloaded the question that those all might be highly related, but they are. Okay, you people are related to fruit flies by your chromosomes. Share about 85% of them. It takes a certain amount of stuff to just be alive. Okay, and that's the observation. 85% of those things are the same. In fact, our experience is more like 95%, and that's the win here. So we're going to talk about what's in this engine to give people some idea how we can do this. It's a very simple idea. There's two things we put together. We put together the compiler technology that the compiler engineers have been building for the last 50 years. Okay? If you're going to deal with large pieces of software, you ignore what the compiler guys do at your peril. It's real simple. You need this machinery. So we've taken a lot of this machinery and integrated it into DMS. Okay? Now that machinery is mostly compiler stuff. Compilers take in source code, they analyze it, they look for special cases, they do code generation from it, they spit out something else. That's what they do. Okay, now if you specialize that to a particular input language and a particular code generation style and a particular kind of set of optimizations and a particular kind of binary output, you get a particular compiler like GCC. Okay, that's a nice thought. Okay, it's pretty useful. There's lots of other compilers built around that. The difference between what we do and those kinds of compilers is we've generalized the daylights out of the boxes. Right? So you need to parse the input languages. Whatever language you need to read, you need to read them from their external textual form that people deal with into an internal form, which essentially are compiler data structures, which I've symbolized by abstract syntax trees up here. Right? So, and you'd like to parameterize that by language definition so you can feed it lots and lots of different languages and have it process them all. You need an analysis engine because you need to ask questions about your software. If you're going to remediate a problem, first of all, you need to know where. So you need analysis machinery, and you can set up general kinds of analysis, okay, and configure them to ask the questions that you want. All right, now, most compilers will emit error messages. In this diagram, you see them coming out over in the right called analysis results. So you might have the tool just focus on analysis and print a report. And we'll see examples of that further on. But more interestingly, what you want the analysis tool is to drive the signal from this analysis results, if I can find it. This arc here from analyze, transform. This is the key interesting arc. Okay, analyze to find my problem. Use the analyzer to drive a change to cause an impact, cause an effect in my system. And we feed that to a transform engine. What the transform engine does, it maps compiler data structures to compiler data structures. Okay, if you look at the way compilers work internally, that's what they do. Those are the middle 5 chapters in any compiler book you'll see, how to map from a high-level form to a low-level form. That's what it is. But you can generalize that, okay, with a notion called program transformations, which we do, and I'll talk about that in the next slide. Then there's the formatting, which in our case is mostly about taking the compiler data structures and converting it back to source code. Because what programmers want is control of their system, put my code in, have something happen to it, have it come back out, have it mostly be my code with improvements in it. So our formatters basically generate source code. So they're kind of funny compared to the kinds of objects, the kinds of things you got a regular compiler. Now, the way we deal with this is we parameterize these boxes, okay, with the various kinds of things it takes to do that. And if you'll see down here, yeah, it looks like we have a damaged arrow in this diagram. There's supposed to be an arrow from this list of language definitions into this rule compiler, and I don't know why it's damaged. Right? In any case, the rule compiler accepts 2 things. It accepts language definitions in the form of what you might think of as BNF augmented with a bunch of other things about how to analyze that language, particular properties it has. And it accepts the tool definition, okay, which is what we want the tool to do, what kind of analysis we want it to perform, how we want it to use that analysis to drive the transformational change. All right? So the stuff in the gray box there stays constant in the same way your operating system stays constant. These pieces are just there. We feed these 2 things in and wiggle them in order to get the effect that we're looking for. And that's the principal value that we think we bring to the table. Here's a piece of machinery that lots of organizations could use, okay, by wiggling these inputs for their particular tasks. All right, so what makes this interesting? Well, there's the fact that the tool can provide some kind of understanding, help me understand the source code by sort of low-level parsers. The compiler data structures make it possible to do algorithmic analysis over the code and get some kind of answers. Okay, and we actually have deep information flow analysis. If you really want to understand what happens in a system, you have to know what information flows in and where does it go and what happens to it. That's a flow analysis question. So fundamentally, flow analysis is core to this, right? Right. The core of this is a transformation engine. I'll talk about that in more detail in just a moment. Okay. And the other issue that makes this tool interesting is not just the sort of theory picture. Okay, it looks nice picture, that's cool, you could find an academic paper. Okay, I wrote one like that about 25 years ago. Okay, but rather because it actually works on real systems and it works on scale. We've actually dealt with systems that have millions of lines of code, multiple languages, mixed languages. There's a computational element underneath. There's a parallel processing engine to support the size of computations we're doing, because doing symbolic computation at the 1 million and 10 million line scale is expensive. There's a parallel processing system underneath DMS. That's all I'm going to say about it today. But I'm happy to talk about it offline. Right? And it's been actively used and enhanced for over a decade, okay, by a small but very clever team, I think. Okay. So let's talk about program transformations. This is not going to be my day. I need to advance this slide to the point where you can see it all. I don't know why I'm not getting it projected the way I want. All right, let's start here. There was an idea back in 1969 that says it would be really cool if we could synthesize programs from scratch. All right, and what these guys said was, you imagine something, that's the requirements bubble over there on the left, and I'll write down some formal specification for it in my formal language, whatever that was. And we all know there's dozens of formal languages have been proposed. And then we'll get some magic engine that takes that formal language spec and generates code at the backside and produces a program. Okay? That idea has both been famously a failure and a success. Okay? The high-level version of it, really high-level requirements and specifications, has been a complete disaster. I don't know if anybody can really do this very well. The low-level version of it has been a gorgeous success to the point where everybody forgets about it. They're called compilers. Right? Everybody has one. Everybody uses one. Nobody thinks about it. It just works. But if you push on the high-level version of it, okay, what you realize is going from a spec to that final program in a single step, like, look, it takes in 2 million lines of spec and it produces a 10 million line program, and it does that in one step. It seems pretty hard, really hard to believe. The only hope you have of doing something like that is say, why don't we do this in stages? Let's somehow incrementally convert that specification into the final implementation by applying a whole bunch of knowledge, which we'll call rules, that map that spec to the code. And on the lower part of the slide, I'm going to show you a little simple version of that. So you can imagine down here in the lower left, you can see we have a little specification. It's written in algebra because this way I don't have to explain the spec language to you. I assume you all have had algebra, right? So that's a specification. And what we want to do is compile it to a more efficient program. Okay, compilation means more efficient for some definition of more efficient. Most people think more means compile to machine instructions. That's one definition. Another one is it just takes less time to run. That's a version of compile, right? Because that's what everybody's really looking for. So on this slide, we're going to do the second one. Takes less time to run. We're going to do that by basically simplifying this program, applying optimizations to it. And the optimizations we apply are all ones you learned in 9th grade. So this first step goes from our simple spec here to the second spec, and it applies the distributive law that you learned in the 9th grade. And then we use a unity multiplier to get rid of 1 times y and convert it to y. And then we apply a few more of these very simple 9th grade transformations you know about to get to our final program. This is a compiled program in the sense that it's better. It's smaller. If you built a dumb interpreter to interpret the left one and the right one would run faster. So it's compiled. So this achieves the idea. It doesn't achieve the sort of scale you want. Think about 20 million of these transformational steps, but I couldn't get those on a slide. So I tried to keep it simple. But this is the sort of idea. We want to take this analog and apply it to software, where the thing over there on the left is a formal spec, or a piece of code, or a piece of object code, any kind of a formal document. And the rules, okay, are pieces of knowledge which legitimately tell you how you can manipulate this program to make a change. So the issue is, how can you give it different language definitions? How can you feed it a lot of rules? All right, well, what does that really look like? This is what transformations look like when you go from the algebra world to the programming world. Right, so this is a transformation that maps from the source domain in COBOL. I have some kind of COBOL program. And what I'd like to do is I'd like to convert this COBOL program into C#. Okay, we can talk about whether this is a good idea or not. It's certainly a popular idea with lots of large mainframe guys right now. Right, so there's lots of interest in that, and being, well, a money-grubbing company, we help people do this kind of thing. So how do you get from COBOL to C#? Well, the answer is convert each of the constructs in COBOL into a corresponding construct in C#. At least that will give you equivalence. And so here's a rule that does a piece of that. This rule takes care of the special case in COBOL where you can say add some variable to some other variable. That's a COBOL phrase, legal, for some source expression and some target expression and some target variable. Right? That add v1 to v2 in COBOL rewrites to the slot called v2 in some object, okay, is updated by the value that you computed from v1 from whatever object it came from. So hiding behind this thing is an analysis. That \object thing is a metacode. It says I need to go off and do an analysis to figure out where we decided to put this object, okay, in the target system. So it's hiding an analysis there. There's a second analysis there that says you can only do this if v2 is actually represented in the target system as an integer. It doesn't work if this is a decimal number because C# doesn't do decimal add plus. It won't do that. Okay? So what we see on this particular transformation is a syntax directed on the source. If you see this piece of syntax here, replace it by that piece of syntax there. That's mathematics. It's called equational equivalence. A equals B. Replace this by that. Okay, do some analysis to figure out what to replace it with, and do some analysis to add some conditions, like if represented as integer. If you take that transformation and you apply it to the before piece of COBOL down there at the bottom, and you run it with some other transforms that are allowed to actually do the object lookups and things like that, you can get out something like invoice.shipTotal plus equals, that should say plus equals order.widgetCount. So there's a transformation. All right, now, we write those transformations as source text because we're engineers and we don't know how to read compiler data structures easily. As engineers, we want to work with that. But the tool can't work with text. It has to work with compiler data structures. And so the way it handles this kind of stuff is it takes those rewrite rules and it transforms the same kind of compiler data structures as the actual source code so it can match them all up. And that's how it works internally. So it maps from that structure to that structure. OK. Now, if I give you one rule, you're not a mathematician. OK, x plus 0 won't get you a job, OK, at Johns Hopkins. Right? So if you want to be really good at mathematics, you have to take a lot of courses. You have to learn the various kinds of mathematical systems there are, the various ways to write down formalisms, the various ways to manipulate those things. There's a bunch of rules. And if you're going to be really good at it, you're going to spend a long time doing this. And if you do, you can do spectacular things with mathematics. DMS is the same way. If you give it one rule, you get a cute example like the one I had in our previous slide, but it's not really impressive by itself. You get 3 rules, yeah, you don't get much. You get 50 rules, you start to get to the place where you can do things like building test coverage tools, and we'll see some examples of that down the road. And you give it several thousand rules, and you can do spectacular things. You can move the pyramids. Okay, in particular, you can move the B2. Right? It's just a matter of scale. So number of rules matters. Now, we talked about the transformational aspect of the tool. Okay, it's supported by a bunch of analysis engines. What I said before was that flow analysis is important. How does information flow throughout your system? We don't do anything magic here. Okay, what we do is we implement the compiler technology you can find in the Stanford computer science bookstore. Go to the back wall, where there's a bunch of compiler books, pick up the first book on the left, implement that, throw that one away, pick up the second book, implement that, throw that one away, repeat. We're about halfway down the wall. Right? Fundamentally, what they say is you need to figure out how information flows throughout your system. Okay, so computing flow graphs, information flows, use definition chains, definition use chains, points to analysis, all these things are interesting. So this is an example of a flow graph, okay, decorated with data flows, okay, for that little tiny spot up there at the very top, which I'm sure you can't read unless your eyesight's far better than mine, okay, that's a Fibonacci program. All right, this is all the stuff, whoops. This graph that you get is all the information flows that happen inside that Fibonacci program. My first comment is, man, no wonder programming is hard. Okay, you have to understand all these kinds of relationships in some sense in order to believe this program is right. Right? If you can collect this kind of information flows, then you can discover that some event here in your code at this point can have an impact downstream on there, whereas that event doesn't have any downstream impact on this part. And being able to just simply separate the part of the program which is important for the task you care about is fundamental just to focusing your attention. Right? So you need the flow analysis just to help find out where things happen, to help separate things that are irrelevant to you for things that are not irrelevant to you, and for understanding how information flows around the entire system. So this machinery is built into DMS, okay, and it's been applied to a number of different languages. It's a generic subsystem, and we connect it to different language by providing some extra information with language definitions. If you have this language definition, here's how you feed the flow analysis machinery. Here's another analyzer. This is a range analysis. How big is this value? Okay, why would I want to know this? Well, I want to know if I'm going to overflow. I want to know if I exceed my storage demand on some array. I want to know how much storage to allocate for this particular variable. I'd like to know all kinds of things. Right, so this analysis is done using abstract interpretation over symbolic range constraints. A symbolic range constraint is a very short formula, okay, involving three constants, A, B, and C, and 2 program variables, X and Y. And it says, I can discover this particular property is true of this pair of variables at some point in the code. And we have examples of that up here. Okay, here's a small program. Okay, going into the program, we know nothing at all. Okay, coming out of this first conditional, what we know is minus I is less than minus 4. That's a complicated way. When you write this down, it's a complicated way to say I is greater than or equal to 4. Shouldn't surprise you from the conditional, right? And likewise, I is less than or equal to 3 if you come out this way on the branch. If you take these, if you take these range constraints and you propagate them through the various kinds of statements that occur here, you end up collecting more information as you go through the program. Think of this as symbolic simulation of what's happening in the code. What do I know about the answers? In this case, we got a fork here coming off this way, collects information. We have a fork coming off this way. And down here we have a join where these two set of facts come together. And so all we know at this point is the intersection between those 2 sets of facts. We take that intersection, we end up down here with this particular fact that says minus k is less than or equal to minus 3, and that might not seem very exciting, So you think about it, well, what that really means is k must be greater than 3, okay, and there's no upper bound on k. What that means is that this array access down here is going to fail because there has to be an upper bound on k. So in essence, this kind of analysis helps you find things like subscript faults. All right, so just an example. All right, so that's an analysis. So what's in the engine? Well, it's a pile of gears. It's a toolkit. You screw them together the way you want to get the output that you're looking for. It contains parsers, contains pretty printers, which are anti-parsers. That's all they are, just inverse functions. Okay. It contains a surprising number of mature front ends for tough languages. Okay. There are about 4 or 5 C++ parsers on the planet. We have one of them, right, because of the machinery we built underneath it. So C++, C, Python, Fortran, Ada, ABAP. Okay, we have a large number of well-tested front ends that we've applied in serious commercial contexts, right? It takes a long time to get the details on those things right. We've spent about the last 5 years busy tuning our C++ front end to try and deal with all the various weird peccadillos that show up when you deal with C++ and you deal with the dialects that come with C++. Okay, Visual Studio C++ is not the same, okay, as GCC C++. They're different in subtle ways, and your reasoning turns out to be different depending on which compiler you're using, right? There's this part down here called a procedural API. This is what you find in the compiler books. I have a tree, I have a symbol table, I have a flow graph, and here's a bunch of APIs I can use to manipulate those things. That's the very bottom of our system. It shouldn't surprise anybody, okay? It's what you do if you need a compiler. We try not to use it. Okay, what we try and use instead is we try and use these various kinds of analyzers. We've talked about them: control flow, data flow, symbolic range analysis. And we try and use the rewrite engine. Okay, this pattern matching language says you can, if you see this, replace it by that. Okay, either in different from one language to another or from the same language to itself for optimization purposes, right? And as I said at the bottom of the stack, I lied. I said I was only going to say it once. I lied. There's a parallel programming language at the bottom in a discussion. Main point is a big pile of gears. You screw them together to get the effect you're looking for. So this is kind of another view of it. Okay, so we've got that compiler front end. It actually reads these various definitions, dumps them into a set of internal databases, and they drive essentially the evaluators and the transformers. And then we have a set of separate subsystems down here that actually carry off these, analyses in the abstract and can be tied to a particular programming language by the description that we gave it on that input over there. Okay, so we're going to take some look at some other applications of DMS, just to give us some sense of the kinds of things we've done with it. Okay. We found that, well, a lot of people want to have really good information with their system, and they want to have it now. Sometimes you can't get really good information fast. So maybe it'd be okay to get pretty good information really fast, right? So we built a thing called a search engine. This is a tool for fishing around in large bodies of text. Okay, it doesn't have any really deep knowledge of that text. In fact, basically what it does, it takes the source code and lexes it according to the lexemes of the language. But when you've got 15 different languages, you can lex them all according to a specific language. Then you can build a query language over those lexemes, and now you can search for things. This is a search in a language called, I think this is natural? This is natural. This is a 4GL. This is a programming language for business stuff, okay, in the 1985s, 1970s and 80s. Okay, and we wanted to find out was how many input screens did this thing have, okay, across this 1.3 million lines of code. Okay, the customer came to us and said, we think we have, I forgot what they said, we think we have something on the order of 1,600 input screens, right, in our application. We'd like you to convert it. Now please give us a fixed price bid for this based upon 1,600 screens. Would you trust them? Right? The answer is no. Go check it out for yourself. Okay. We found, this says we found 1,112 of these things. Okay, these are not the input screens they were talking about, but they're input screens. So there's another 1,000 screens that they didn't tell us about. So this is really good information. So this is good information really fast. So this is a search across a system. You can kind of think of this as Google for code. Okay, only it's internal as opposed to external. Right? I think you guys already have a tool to do something like this. This is used for fishing around internally. So this is okay information, but really fast. We talked about the mainframe problem, the guys with the 10 million lines of COBOL. Okay, what they wanted essentially was a picture like this, and this, in fact, is exactly the picture we gave them. Okay, so this is a COBOL program here in the center. Okay, and it reads this database, it reads this database, It writes to this flat file, okay, and it's controlled by this piece of JCL. So basically it says, you point me to a module, and I'll tell you how it's connected to its neighbors. Okay, and they got, of course, they can, a little search mechanism over here so they can figure out which components they want to look at. This allows them to look at their 18,000 components, one small subgraph at a time, and get some sense. If I make a change to this program, who do I have to worry about? So it's a very simple answer, both in concept and in terms of delivery. Very hard answer to get because you got to read all this stuff and get all the details right, do this flow analysis across these 10 million lines of code. All right, here's a second kind of analysis done with DMS. Okay, people have clones in their code. Anybody here not clone any code? No hands. Okay, it's a surprise. Everybody knows they have clones. They don't know how much. Okay, it's a bar bet I'll take with anybody. You got 10% or more clones in your code. Anybody, I'll take the bet. Right? All right. Reason we know that is we've been running this tool for detecting clones for the last 10 years over everything you can imagine, from Python to Fortran to Visual Basic 6. Okay, and it comes out 10 to 20% or worse on everything we see. Okay, the Sun guys, the only guys that beat it, it was 9.87%. Okay, with the JDK. Somebody had actually been working on it hard. I'm impressed. So here's a tool for locating duplicated code. Somebody's wrote something they thought was useful, and they cloned it someplace else. The good news about that is it's software reuse. It makes them more effective. The bad news about it is bug reuse. Okay, whatever you cloned has some kind of problem in it in the future. Maybe it's not actually wrong. Okay, but if you change your mind about the architecture and it contains an architecture decision and you replicate it, you're in trouble. Here's another way to think about it. Imagine your source code base is 20% redundant. What that means, if you pick a random line of code in it somewhere, there's a 20% chance that someplace else in that system that same line of code exists. And you decide you have to change that random line of code to improve it. That means there's a 20% chance that someplace else in the system is another line of code that you should fix. How many of you know where that other line is? So what you'd like to have is a tool for locating where all these clones are, telling you where they are, and showing them to you. All right? So here's an example from Python. Okay, this is the this is the BioPython test, something like that. And people could see down here if they look. They can see it says 11.1, 11.7% redundant. Okay, across something like 202,000 lines of code. This is a small system from our point of view. These things get bigger, this number goes up. So this is just a summary report from a tool, okay, as a sample of a clone. I didn't take one from Python, I took one from PHP, just to show that we're different. We have a PHP front end for DMS. So this is a clone piece of code. Okay, you can see it's occurred in 3 places. Okay, it's in 3 separate files. Okay, these clones happen to be exactly the same. 100% identical, copy, paste, done. Okay, most of them are not. Okay, most of them are slightly different. The tool knows how to detect that. Okay, this kind of tool works on any language that DMS can process. And if we run into a language that DMS can't process for this, well, we define the input to it, and then this runs. We had a customer in Austin that said, I think I've got clones in my code, and I'd like to manage them. And they came to us, and they worked with us for a while. After they did this exercise, they drew a size curve on their system. And there's a size curve, and it went up, and I'm not very surprised by this. Systems get bigger. And then it did something that's shocking in the software world. It went down. Okay? Guess what that inflection point is? They started using the clone detector. Right? So here's a way to manage your system size. Here's a way to cut your engineering costs on large-scale systems. Go find the clones, go manage the codes, control the clones, make sure you're processing the clones. Okay? He was very happy with this as a tool. All right, so that's kind of how things are similar in the big. All right, it's also true that you like to see how things are similar in the small. Everybody uses the Diff tool. Okay, take 2 files, one in which I've edited, and show me how they're different. Now what Diff does is it shows you how they're different on a line-by-line basis. Nobody I know of uses a line editor. So this seems like really the wrong answer. Okay, if you think about the way people work with code, what they do is they say, here's an expression or a statement or a block, and I need to do something to this. I need to move it, I need to modify it, I need to change it, I need to delete it, I need to insert it, I need to copy it. They think like that. At least I think like that. I don't know about the rest of the world. And so a tool that told me what the differences between 2 pieces of code in that vocabulary seems like it would be much more effective. You change this variable. You move this block of code. not this line's different somehow. Okay, so an engine that we built called the Smart Differencer uses the same machinery as the clone detector does in the small. Look for two things that are the same. Okay, and instead of showing you what's the same, it shows you what's not the same. It shows you the complement. It's just the other answer. Right? And that gives you essentially a Levenshtein differences between the abstract syntax trees. What's the smallest set of changes you might make to get from one tree to the other? And you can think of that as being a plausible editing path. How did he modify this program to get to that? And it comes out and hands you things like this block of code got moved. One of its more interesting aspects is you renamed all the variables in this scope this way, as opposed to I edited 47 places. Okay? It's completely insensitive to the formatting and the comments, so if you change the formatting of the text, it doesn't get fooled by any of that stuff. So this is a really useful tool in the small. Okay, here's kind of a quick example. Okay, this is done on COBOL. All right, so we look over here on the left, we have an original piece of code. We look over here on the right, we have a modified piece of code. And what you'll see is that term name got renamed consistently to term title throughout this piece of code. So essentially it did the diff, painted up these two screens that here's where the difference is so that you can see it. If you're a code reviewer and you have to see how your code got changed, this is a much, much easier way to see what actually happened. Okay, well, we've talked about migrations. Okay, and so we use this sort of like nice scene we've seen from nature shows about this guy leading these birds on migration, and then we have kind of go to the stealth bomber up here in the corner. Whoop. Right, so we've talked about migrations. I think I've made that point. Right, so if you need to move from one system to another, change platforms, change languages, this does all that. Right. Now, that was transformation as opposed to analysis. You can use transformation to support analysis. Okay, in particular, you can use transformation to instrument your code to collect data as it runs to help you decide how good it is. So a fundamental question before I ship my code is, did I test it? Everybody says you should do unit testing. We all buy that, right? You all write unit tests. But do you know how much of your code you tested? Okay, if you tested 5 lines of your code with your 1,000 unit tests, I don't want to ship it. I should be afraid. So you'd like to have a tool that essentially says, tell me what part of my code got executed by my tests. The tests all pass, and most of my code got executed, I might feel comfortable about shipping it. The tests all pass, and hardly any of the code got executed, I should be scared to death. So I have no idea what that line of code that I never executed does. I just don't know. I have no test. So what a test coverage tool does, it instruments the code to collect execution information. I got here. It does that massively over the entire system. You run the code, it collects all the probes, it displays them in a nice format, paints them up in a nice picture like this. So the red part here is a piece of the C++ code that did not get executed, meaning red for stop, and green means this stuff got executed, green for go. All right, you can use that kind of instrumentation to do not only test coverage, but profiling, both counting and timing profiling. Okay, and the style's the same. Instrument the program language, whatever the kinds of probes you need for this particular language. So the transformations vary a little bit, but the style doesn't change at all. Okay. Some of our customers ship intellectual property to each other. They want the receiver to use it, but they don't want them to understand it, and they don't want them to ship it again. So what they actually want to do is to take the code which is shipped and scramble it in a way that makes it impossible for a human engineer to know what's going on. Oops. So here's a piece of Verilog. This is a chip design. Some guy says, I want to design my chip and I want to sell it to you, and I want you to integrate into your chip. But I don't want you to ship it to a third party. So what they'll do instead of shipping that thing is they'll ship you something like this. This is code obfuscation. Take the code, scramble it, change all the names, remove all the formatting, remove all the stuff which are cues for people. Okay, so that they can ship this and have some kind of technical support for the intellectual property safety. All right, there's a lot of other applications of DMS that we've done. Okay, I'm not going to go through them in detail. I'm leaving the slides behind so people can look at it. They can take a look at the slide in general. Okay, but they cover the spectrum from embedded systems, okay, to SOA, to other migrations, okay, to generating vector machine code, okay, for parallel machines. These are all done with DMS, basically by carrying out transformations on source code. We get continually asked, can you do other new things? People show up and ask us all kinds of questions. Some we say, yeah, we think so, some we can't. These are sort of things that we're talking about with people in sort of serious ways at the moment. okay, migrating applications from mainframes. We have a bid into the University of California at Santa Barbara to migrate their student information system off of natural and a mainframe into C#, right? A particular task that they want done, right? Control developments. Control development costs by minimizing the software base. Okay, we have a customer that's got 55 million lines of Java code. They're pretty sure half of it's dead. They don't know which half. Help them find it, help remove it. That's a big task to do by hand. Okay, I got multi-core CPUs. We're talking to we'll just say a big packet switching vendor. Okay, they've built themselves a packet switching piece of software which they make a lot of money off of, and it was designed around a single-threaded execution model. Suddenly they have 32 CPUs, and their code's not ready for it. What now, brown cow? Okay, you need to analyze the system at scale to understand where you can break it apart and what you might do to parallelize the thing, right? Well, U.S. Navy came to us a while ago and said, we're buying software from Czechoslovakia because we hate paying money to Lockheed. Okay, and the good news, it's cheap. And the bad news, we don't trust it. So now the question is, can you find malicious software in there? That's not an easy task to do, but you need to build tools to analyze the stuff and help them poke around, so on and so forth. We're currently talking to a university who wants to take C code, okay, for high-speed image processing algorithms, pick out the inner loops and convert those inner loops into FPGA so they can build basically a co-design system, okay, in which they can have low-speed C code and high-speed FPGA for the core of the algorithms. That whole trick is just basically driven off the flow analysis stuff. That graph you saw for the Fibonacci is perfect for what they want to do. So I got invited out here after a conversation with some other folks at Google. Okay, and so I thought I'd put one possible Google application to this. Okay, and as I understand it, there's a building process, a construction process that says I have a very large library of support utilities, I have a large number of applications, and there's a dependency network between them. And we'd like to have as a build process that says, okay, when I touch one of these things on which something else is dependent, okay, that all the things downstream get compiled. That's good. We all call it make or whatever it is you happen to do. Okay, and so here we have a model in which if you change Z, we'd like to recompile Y and Q and G and then A. Okay, that guarantees that when somebody modifies Z that A gets updated. The problem with it is it's granular. Okay, as it's posed on almost everybody's world, it's the dependency, the dependency is based upon not the details of Z, but rather Z itself as a thing. Okay, so it says Y depends upon Z as a whole. So if anything in Z changes, you rebuild Y, even if Y didn't use the thing that Z changed. So here we have an example. If you look inside, what you see is Z has some subcomponents, Z1 and Z2, and Y depends really on Z1. Okay, M depends upon Z2. Now if I change Z2, the question is, do I want to rebuild A? The answer is no, I really don't want to do that. And the secret to doing that is essentially something like the smart differencer. What you want to understand is, what's the difference between the old Z and the new Z? So you can say, hey, this is where the changes got made, here's Z2. And then you want to look at the dependence relationships between Z and Y and Z and M and say, does Y actually use Z2? No, you don't have to rebuild this. So you can build a smarter make by looking at more fine grain, okay, in the code, okay, and looking at dependencies. It doesn't change the fundamental model how you build things. It changes the details of how you do it, and it cuts the cost dramatically. Well, we think, anyway. Especially if you do this on the scale I think you guys are doing it. Okay. All right, so we've talked about a piece of machinery, okay? We haven't talked about sort of the ideas behind it, drivers behind it, okay? We think that not only is the machinery useful, but our perspective as a company is useful. Okay, we've been doing this for 15 years. We think about this differently than most people do at this stage of the game. Because we ask, what kind of hammer can I hit it with, not how can I do it with a team of people? Okay, and it takes a while to get used to that idea, because it's amazing how many different ways you can hit it with this kind of hammer if you think about it hard. Okay, the engine, we bring the idea that you need semantically precise analysis as opposed to people precise analysis. People are good, they're not good at scale, right? That you want to deal with very large artifacts, okay, with automated engines. Okay, that you should build an engine, okay, one uniform piece of machinery to carry off this kind of work. And that you can actually use that engine, you can amortize its cost across lots and lots and lots of different kinds of tools. Okay, it's surprising how many different kinds of tools, right? And it's also interesting that by using these tools, we've managed to carry off some tasks that most people consider to be almost impossible. Most of our customers have come to us after they tried to do it themselves and failed. Okay, the B2 exercise, they tried to do it internally by hand twice before they came to us. And they said, basically, they're going to give us the business because we look weird, right? We don't look like we did it the way other people did it, and the way other people did it didn't work, right? It was a really strange reason to get a piece of business, but it worked out for everybody, right? All right, point is, we do hard with this kind of machine. We do sort of very surprising things that people normally think are impossible, right? In practice, we're a small company, okay? And this only works when we find a partner that has a specific task of his own, okay, and he wants to bring somebody to the table. So we actually work with the integrators or the other guy on the other side of the wall to carry off the task. So usually we provide them lots of advice. Here's a piece of machinery. We might build some pieces of it. They might build some pieces of it. We might go through lots of training. It's an interactive process, okay, with our partners. All right, so lessons. One, software is bigger than you are. Worse, it's getting bigger, right? It's expanding at the speed of light. Can you catch, if you run a light way out to it, are you going to catch the edge of the galaxy? Okay, the key technologies for doing this are really simple, really simple. You got to be able to parse stuff. Duh. Okay, you have to be able to analyze it. You have to worry about data flows at scale, all kinds of data flows. Got to fundamentally implement all that and make it available to build tools on top of it. You need to be able to carry out transformation for change. You don't want to go to the doctor's office for an analysis. You want to go there for a cure. Tie analysis to change. That, I think, if anything you walk away from this talk, it's tie analysis to change. That's what tools are really good at. Right? You're always going to need a custom tool because your situation's different than everybody else. You grew up the way you did, okay, your perspective is the way it is, you have a bunch of historical baggage. You need a tool that deals with the world that you're in. That means you need a custom tool. And you're never going to find it lying in the gutter. Okay? You'll have to build it. All right? So I think this is another insight. It's hard to build. You don't want to build this infrastructure by hand. It's way too expensive. I will scream if I hear another guy at a working conference on reverse engineering saying, I'd like to redesign the system, and if I just had a parser. I will scream if I hear that again. Right? They're always there. They don't seem to understand that even if you have a parser, okay, it's like climbing the Himalaya, it's like climbing Mount Everest. The first 8,000 feet's easy. Anybody can do it with a backpack. The last 19,000 feet requires a completely different technology to get up to the peak. Completely different game, right? Looks easy. Yeah, first 8,000 feet is easy. Any cloud can do it. But that doesn't matter. So the infrastructure is expensive to build. It's hard. It has scale. You need generic analysis. You need robust language front ends. You need all stuff to fit together. Okay. Bottom line here is DMS is an engine for doing this. The reason I go around and proselytize is because there are no other engines on the planet that look anything like this at this kind of scale that I know of. There are some research systems called Stratego and Tixel, which you can download for free. And they say this, they tell the same stories, but they don't apply them like this. Okay, they aren't going off and fighting the battles that people have, the real battles. You know, can you really parse C++? Can you really do 10 million lines of code? Can you do this flow analysis? Can you do a call graph for this entire system? They don't do those kinds of things. It takes an investment in the machinery for 15 years to get here. Okay, I'm open for questions. I understand there's an audience here, okay, with mutes, so you may have to turn your mic on if you want to ask your question. And we have a mic here for people to step up and ask if they wish.
I was curious when you were talking about looking for duplicate sections in the code or like copy-pasted code. Are you able to do that even if it's not identical code, if it's just similar in structure or maybe close to the same code?
Yeah, we detect what we call exact clones and what are called near-miss clones. Now, what we don't detect are semantically equivalent clones. It doesn't detect two pieces of code which compute the same thing but do it in radically different ways. It detects pieces of code that people have literally copied and modified. Okay, it's really a weird perspective to realize what makes clones findable is the fact that somebody stole them in the act of stealing them and made them visible. Okay, but so it's not finding semantically equivalent things, it's finding syntactically equivalent things that somebody has stolen. So the smart part of the clone detector, weirdly enough, isn't the clone detector. It's the guy that stole the code. He made it visible. He went and identified this blob of code, this thing with this formal's boundary. Said, no, here's the line, here's the part which is good, pull it out, set it over here. And the moment he does that, now you can see the boundaries, and they're drawn black. Right? Microphone?
The example of smart differencing that you showed, didn't seem very different from a line difference. So I guess that's probably because you chose a simple example. But In cases of semantic differences, have you thought about how to show that visually? Because
well, so let's talk about the example for a moment. Okay, I mean, you're right. If you were to do this line by line, a pure line detector might actually detect this. Okay, the question is, what did it say? Okay, a line-oriented detector wouldn't draw those green patches. It would simply say that line 10900 was different and line 11030 was different. What our tool says is the variable name, term name, has been renamed to term title throughout this block of code. That's all it says. It says it once. So it really isn't a line-oriented answer. Okay, you can't see it from this particular one. Okay, I'll go back and ask your other part of the question again.
The question I was getting to is if you're finding differences that show the difference in an abstract syntax tree representation, how do you actually surface that back so that it makes sense to people?
We don't show it. You never show an abstract syntax tree to a person. That doesn't work. Okay, that's the reason for the pretty printers. What the pretty printers do is allow us to take an arbitrary internal data structure and convert it back to source code. And so the kind of thing you'll see coming out of the abstracts, out of the smart differencer, if you tell it to do this, is I move this block of code from here to there, and it'll actually show the block of code. It's this block of code. And it might start in the middle of a line and end in the middle of a line because it's pulling out the abstract syntax tree, not the lines. Right? So it shows you the source text the way you would see it as a programmer. I can only put up one slide here and have time, right? So.
I was just wondering, what's the largest system you ever worked with? You were talking about, apply this to Google. I don't know how many lines of code we have, maybe 50 million, 100 million, things like that. Have you done anything like that?
Well, I think the right way to ask the question, what's the largest system we work with? Okay, I mean, my suspicion is that you don't have a single monolithic 50 million line system. You probably have a lot of 5 to 10 million line systems. Okay, you may prove me wrong. Okay, we did have, well, the packet switching customer had 35 million lines of C code as a single system. Okay, and they stretched us to the hilt. And one of the problems there was to do what's called a points to analysis. What you want to know is for each pointer in the system, what could it point to? This is what's called a may analysis. This may point to X, it may point to Y. Okay, and we essentially had to do that analysis across all 35 million lines of code. Okay, university papers weren't good enough. Okay, we actually did something to do this. It ran for, I think it was 6.5 days on an 8-core machine. Okay, and used 90 gigabytes of RAM to compute this answer. Probably not big by your standards, it was big by ours. Okay, to compute this answer. That's the biggest thing we've dealt with. Okay, as a single monolith. I had a conversation, an eye-opening conversation with the CIO at Metropolitan Life back in 1995 when I first started the business. Okay, at that time we had no technology at all, and so we walked around proselytizing. Okay, so we went to visit these guys because, well, they seemed like interesting customers. All right, and I asked this guy, so how much code do you have? He says, I have 100 million lines of COBOL. Right? I said, oh. He points out the window. We're in New York. He points out the window, this building, 3 buildings away. You see that building over there? He says, it's full of COBOL programmers. Okay, I need to control that. He says, what's the problem? He says, it isn't the 100 million lines of code that makes me crazy. It's growing at 5 million lines a year. That was 1995. God knows where that man is now. He's probably retired. But his successor has got 200 million lines of COBOL. We went out to visit the Social Security Administration about 2 months ago. They do have 200 million lines of COBOL. Okay, and that's the mainframe part. Then there's the external facing part, and they've been doing all this distributed stuff in C# and Java. 200 million lines of COBOL. It's breathtaking. I will say that we're probably not very good at this. We're probably better than anybody else on the planet. Okay, it's a tough choice, and one of our struggles as a technology company is to try and make sure that we stay on that curve, that we follow people up as their systems get big, right? Because otherwise we're all headed for collapse. Okay, black holes happen. Okay, when the amount of mass in there gets to be too big, and then you're dead. You don't want to be there when you get a Schwarzschild radius effect, right? Anybody else?
Thank you.